Okay, we are back. So let's keep going. Number 15. So this is the second portion, right, of the prerequisite review. Number 15, we have to solve the quadratic equation. No, sorry. For the following quadratic equation, we just have to find the discriminant. So discriminant, we have to recall, is just a portion of the quadratic formula. So here is the quadratic formula. For any quadratic equation, y equals ax squared plus bx plus c. For any quadratic equation, if I set that equal to 0, then now I can use the quadratic formula, right? And the quadratic formula is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. That's how we solve, or one of the methods we can use to solve a quadratic formula once we set it equal to 0. And the reason I wrote that down here is because we need to know where does that a, b, and c come from in the quadratic formula. And I just wanted you to recall that the a is the coefficient of your quadratic term, right, the one that has the x squared. The b is the coefficient of your linear term, the term that has the x to the first power. And c is the constant, meaning the term that does not have a variable, okay? So this is your quadratic formula. So back to the discriminant. The discriminant discriminates among the type and number of solutions I have. So the discriminant will just be what's underneath the square root. A common mistake from students is when they're asked to use the discriminant, they actually also use the square root, which we do not. We only want the radicand, meaning what's underneath the square root. So the discriminant is just the b squared minus 4ac portion. How does it discriminate? Well, think about it. If when you put that in your calculator, you get a positive number, you're going to have the square root of a positive number, right? So square root, where can I write that down? Let's do, what if I do that? So when my discriminant, b squared minus, 4ac, if my discriminant gives me a number greater than 0, meaning a positive number, right, that means positive, then I have two possibilities. But I already know for sure I'm going to have two real solutions, right? Because if I have a positive number underneath the square root, I can take a square root of a positive number no matter what and get a plus or a minus real number. Now, is that number going to be a rational number? I don't know, right? That's something we'll have to look at, right? So we have two solutions here. Two possibilities, two solutions, they're two real and they could be either. So they're going to be either rational or irrational. What do I mean? Rational is going to be when you can take the square root. So you can square root the number. For example, if I end up with a b squared minus 4ac, if I end up with, for example, a 25, well, the square root of 25 equals 5, right? That's what I mean by a rational. I can take a square root, as opposed to you cannot simplify nicely with the square root. You would end up with an irrational number, meaning a decimal that never ends and never repeats. So that, for example, would be if I had my b squared minus 4ac, maybe it will give me 13, right? Well, the square root of 13, when you put that in your calculator, square root of 13, Notice how the calculator gives me a decimal. And you're going to say, well, that ends. Well, it technically doesn't, right? Because this here is just going to be keeping going, right? It's a decimal that keeps going. It never ends and never repeats. That's what we call an irrational number, okay? 13 is the square root of 13 is irrational. So this one is what am I going to tell you here? The square root of 13 is about, right, 3.6055512, etc. Right? So it's a decimal that never repeats, never ends, as opposed to this. So when your discriminant is a greater than 0, meaning positive, you have two real solutions for sure. What type of real solution? Either rational, in which case it means you can take the square root of that number that you get, or irrational, meaning you cannot take a nice square root because it's not a perfect square. Okay? Not a perfect square is really what I should have told you there. That would have worked perfectly, wouldn't it? All right. Next case scenario. B squared minus 4ac is less than 0. So here we said that means positive, that means negative. So you have a negative number. Well, if you have a negative number underneath the square root, you know that you cannot take the square root of a negative number and end up with a real number. You would end up with two complex, we call those complex solutions. Okay, so why complex? Because you're going to end up with a number that has a real and an imaginary part in it. Really what that means is you're just going to end up with a solution that has an I in it, okay? And the last scenario, but you still have two of them, right? But you got two complex solutions with an I in it. The last scenario is when b squared minus 4ac equals 0. Well, if that's equal to 0, the square root of 0 is 0, well, then I don't have a plus or a minus anymore, right? Positive 0, negative 0, no matter what, that's still just going to be a 0, right? So then we just have, that's the case where we have one repeated solution. And if you watch the previous video, one repeated real solution. And if you watch the previous video, you know what I mean by that. And let me go back to the example I looked at, if I can find it. It was right there. We had to solve number 11. We had to solve this. And we had started with a cubic, so we knew we were looking for 3 solutions. But when we were done, we only had x equals negative 4 and x equals 4. And we said, uh-oh, trouble in paradise, right? Because we only have 2 and we needed 3. But then we realized that this one was a repeated one. We had it twice. So even though it's still x equals 4 as a solution, we had a multiplicity of 2. So it counts twice, and then this one once, right? That's what I mean when I say that when you have a 0, you're going to end up with one repeated real solution, right? You're going to have it twice. Okay, so those are our 3 case scenarios, and let's see what we get here. All right, so before we can do the discriminant, by the way, our quadratic equation has to be set equal to 0. Well, this one is not, right? We have stuff here. It's not a 0. So we're going to add 3x to both sides, and then add 2. And you're going to do that to your like terms, right? So I'm not going to add 2 to this guy, for example, right? Because 2 is a constant. It has to be put with the constant. Both of those cancel, and now they're equal to 0. So I have 3x squared. 15 plus 3 will be 18x, and then 25 plus 2 will be 27. Okay. This is now my quadratic in standard form, equal to 0. So now I can figure out what my A, B, and C are. So A is 3. And I'm not sure if I need to write that down, but I'm going to write it down for the first time. A is 3, B is 18, C is 27. And now we're going to put that in our discriminant, right? So B squared, so B is 18. I want to square that. Notice how I go in the habit of putting parentheses around my numbers before I square them. If this would be a negative and I would not put my parentheses, I would end up with something wrong, right? Because then the negative wouldn't be squared, just a number. So it's just a good habit to do. Put your parentheses around your numbers before you square them, especially for the discriminant here or the quadratic formula. So 18 squared, my B squared, then minus 4 times the A, and A is 3, times the C, and C is 27. Okay, I'm going to get my calculator, and I'm going to type that in there. What am I doing here? I don't want to. Okay. So 18, and I'm going to square that. And then I want minus 4 times 3. Notice how like I told you, I put that all in parentheses just to be safe, so I don't have any issues with negative numbers. An order of operation. Enter, and the answer is 0. Oh, lo and behold, we have a 0. And remember what we said, if this is 0, we're going to end up with one repeated real solution, right? So the discriminant is 0, and it doesn't ask us, but it doesn't hurt for us to know that and write it down. Therefore, those 3 little dots placed in a triangle shape like that are actually a mathematical symbol. It's not something that I made up. It's actually a mathematical symbol for the word therefore. So in math, we like to write everything in short, symbolized format, right? It makes it quicker to write. So instead of writing that long word therefore every time, you're going to see me use the mathematical symbol for it. It's 3 little dots, and it has to be placed in this format like a triangle. Not like that, right? That wouldn't be therefore. It has to be in this format, and that means therefore. Okay, so you're going to see me do that a lot, so probably a good idea to make sure we know what it is. So therefore, we're going to end up with one repeated real solution. And again, we were not asked to say that, right? But it doesn't hurt for us to say it. All right, here we have to solve. We solve, and we want the roots in simplest form using the quadratic formula. So we are not given options here on the method. We are told to use the quadratic formula. Remember, it has to be set equal to 0 first. So let's do that. So we're going to add 20x to both sides. So I'm going to have 4x squared. Add 20 will be then plus 20x, and then plus 45. Notice how I kind of squeeze that 20 between them here, because I want that in standard form. Quadratic term first, linear term next, constant last. Okay? And now we need the quadratic formula. So my a value is 4, my b value is 20, my c value is 45. And so it's x equals negative my b value, so my b value is 20, plus or minus the square root of, notice how I put the parentheses as I told you, right? It will be my b value squared, and my b is 20, minus 4 times the a value times the c value. So the a value is a 4, and the c value is a 45. I like to finish my little square root there like that to make sure I show that's where my square root ends. And then all over 2a, so 2 times my a value, which is a 4. Okay, now I'm not going to type all of that in my calculator at once. I'm actually going to do my discriminant first. So in my calculator, negative 20. So now I can drop the parentheses because it didn't have a negative, so I don't have to worry about negative, right? It's just negative 20 plus or minus something, and I'm going to figure out what that something is in my calculator and go ahead and do 2 times 4 is 8. Okay, what's my something? Let's do our discriminant. So the discriminant is, notice how I put those parentheses there, right? So 20 minus 4 times 4 times 45. And that's negative 320. So my discriminant is negative. Well, if it is negative, I already know I'm going to be in this scenario and I'm going to end up with an I in my solution, right? I'm going to have two complex solutions. Okay, so if I have an I, that's what that negative will be. The square root of a negative 1 is just I, so it's going to come out as an I. Then I need to figure out what the square root of 320 is. So the first thing you would always want to do, if you're not sure, just go ahead and do it. See if it's a perfect square. It's not, right? It's not. But we need to simplify that in simplest form. We need to have the root in simplest form, so we cannot switch to a decimal. So we have to ask ourselves something about 320. So let's do that here. 320. So I need to figure out if I have a perfect square as a factor. So divide by 2 is always kind of nice and easy, right? So let's start with that. So that will be 160, right? Okay. Then, well, we can divide by 2 again, right? So that will be 80. And I can divide by 2 again, that will be 40. Divide by 2 again will be 20. I'm going to run out of room. Divide by 2 again will be 10. And divide by 2 again will be 5. Okay, so remember we want to get out of a square root, so we want things paired, right? All of those will give me perfect squares, right? So when I put them all together, I'll get 2 to the 1, 2, 3, 4, 5, 6 power, right? 2 to the 6th times 5. All of that will be equal to my 320, right? Because if I multiply all of those numbers back together, I will get my 320 again. So 1, 2, 3, 4, 5, 6 2's, so 2 to the 6th. And then finally that last 5. Well, what is the square root of 2 to the 6th? So remember, the square root has an index of 2. We don't write it, but we know it's there. And so 6 divided by 2 times 5 will be the fractional version of that. Well, 6 divided by 2 is 3, so that's a 2 cubed. Oh, sorry. Oh, I just did something wrong here. Let's make sure we don't write something wrong here. 6 divided by 2 becomes 2 to the 6 over 2. No more in the square root, right? Because I wrote it as a fractional exponent. I'm going to leave my 5, however, in the square root, because remember in the problem it says we're going to write that as a simplest root. Okay, so this here we said was a 3. And what is 2 cubed? Well, we know what that is, right? That's an 8. So this is what I have. 8 times square root of 5. Okay? So the negative is going to be the I, right? So all of that becomes negative 20, stays there. We haven't done anything with it yet. And then all of that is going to become, remember we said an 8, right? So we have the 8 here. We need an I for that negative. And then finally, we still have the square root of 5 here, right? So we're going to keep that square root of 5. And then all of that over 8. But now, I need to separate my real number from my imaginary portion of it. So I'm going to rewrite them separately, but they're both over 8, right? Because remember, the whole thing was over 8, right? So it's this over 8 and that over 8, right? Why do I do that? Because now I can simplify. 8 and 20 both have a factor of 4, so I can divide them both by 4. So that will give me x equals negative 5, right? Because if I divide by 4, I get 5. Divide that by 4, you get 2. So negative 5 over 2 plus or minus 8 over 8 cancels. I have my I square root of 5. And that will be our solution. Oh, I don't know if you saw that. I hope you see that now. Okay, so simplify that, divide both of those by 4, right? Gives you a negative 5 over 2. Your plus or minus, the 8 here cancel, and so we have left I square root of 5, which is what I have here. And if you remember, I said we go back here. When we said two complex solutions, so why don't we just call them imaginary solution? Well, because they have the I in it, but they're complex because they have a real portion and an imaginary portion. So we cannot just say imaginary solution because that would imply that I don't have that portion, right? But I do. So it's a complex, because it's like a complex sentence in English, you know, it has more than one part. This solution has more than one part. It has a real part and an imaginary part. So we call it complex as opposed to imaginary. All right. Whew, I threw a lot at you in that problem. But that's good, strong review. Okay. For the following quadratic equation, we need to determine the nature. So we really don't know, we don't really care about what the solutions are per se. We just want to know their nature. What are they? Are they two real, rational, irrational? Are they two complex? Are they one repeated real? So to find that, what do? We do the discriminant, right? We're going to see how it discriminates. All right, we have to be careful because there is a negative here. So my A is actually negative 1. My B is 20. And the C is negative 64. All right, B squared minus 4AC would be, okay, so B 20 squared. Okay, I don't have room up here, so I'm going to move that down. Thankful for erasable pens. B squared, so 20 squared minus 4 times negative 1 times negative 64. See how those parentheses are very important when you have those negative, because if you do not put those parentheses there, it would imply that we're subtracting, and we're not. We're multiplying a negative, right? So they're important. All right, so let's do that. Parentheses. 20 squared minus 4 times negative 1 times negative 64. And the answer is 144. And so now we need to know, so we have a positive number, right? So we know it's going to be two real solutions. Are they going to be rational or irrational? Can I take a square root? Is that a perfect square I have, or is it not a perfect square? Well, 144 is definitely a perfect square, right? 144 is a perfect square. Why? Because the square root of 144 equals 12, right? So I'm going to end up with a rational number. That's rational. And so I'm looking real equal rational. No. Equal means non-repeated, right? They're the same. That's not the case. Real unequal rational. Unequals mean two different solutions. So you have two solutions and they're rational. We have two of them because we would end up with a plus or minus and rational. So this is what I want. Okay. I wish they wouldn't say imaginary here, because we do know that they really should say complex, right? We do know that from the problem above and how I explained it to you. It really should be complex, because complex solution means they have an imaginary part and a real part. Okay. Let me erase my board underneath here so I don't make a mess on the back of my paper. All right, number 18. Find the value of k. So this one is a tricky one, but you have to realize that when you're looking at that, what you really want to know is, if I factor this, and I am already told that this is a solution, That means if I already know that that's a solution, that means I already know that x equals 16. Before it became a solution, it had to be a factor. So move that across the equal sign, because minus 16, that had to be true, right? And if that had to be true, that means this had to be a factor. Therefore, I already know that one of those has to be that. Why? Because they tell me that this is a solution. That's given to me. So I don't know if x equals 16 is a solution. The minus 16 is a factor. Okay, so we already know this guy. The next thing we need to ask ourselves is we are looking for k, right? And we know that k is going to come up with the negative 16 times something, and that has to give me k, right? Let's write it differently. Hold on, I'm going to write that differently. K has to be equal to this number times this number, right? So it's going to be negative 16 times something. I don't know what yet. That's what I'm looking for. Here, I will have an x as well, right? I know that for sure, because x times x is going to be my x squared here. Where does that negative 7 come into play? Negative 7x. Well, whatever I multiply here and here has to give me my k value, but when I add them, it has to give me negative 7. So when I do negative 16 plus my mystery number, it has to be equal to negative 7, right? So let's give a name to my mystery number. Let's call my mystery number, I don't know, maybe z. Why not? Let's call it z. So my mystery number here will be z, right? So here is my mystery number, z, this one. Whatever I multiply here and here has to give me k. Multiply them has to give you k. When you add them, it has to give you negative 7. When you add them, it has to give you negative 7. Well, here I have two unknown. I can't do anything with this equation. But this one, I only have one unknown. I can solve that. So I'm going to plus 16 on both sides. And so z is equal to 16 minus 7 is going to be 9. And now I have my mystery number, should be 9. Plus 9. Now, how do I know plus? Because it's a positive 9 I end up. Now let's check. We want to make sure, right? Multiply. Oh, sorry. We have the z mystery number. Never mind. We still don't know our k. But we do know that now. So now we can say this is equal to negative 16 times my mystery number z, which is 9. And then we're going to call our tool here, our calculator. We're going to do negative 16. Notice how I always put my parentheses around those, right? I don't want to mess up anything with my order of operation or anything like that. And it's a negative 144. So k is negative 144. All right. Moving, so let's do that here. Moving to that side. The graph of f is given, so this is f. And we want to know what are all the real solutions of f of x equals 0. So real only because we cannot see imaginary solutions on a real number plane, right? This is a real number plane. All those numbers on the x-axis are real numbers. All those numbers on the y-axis are real numbers. So those are only real values. So we will not see the imaginary solutions on a real number plane. So we only look for real solutions. But the real solution of any function are going to be where the function equals 0, meaning the x-intercepts. X-intercepts, right? Okay. So here I have negative 5, right? So x equals negative 5. is one of my solutions. Notice how the graph, the function, the curve, just goes straight through it, right? It doesn't do any weird curving, U-shape, anything, just nicely straight through it. That's an indication to you that this is only one solution that you have there, x equals -5. Here, x equals 0 is another solution, right? It goes through at x equals 0. Same thing, see how it goes straight, nicely through? It doesn't do any curving, any weird things. One time. And then we have another one right there at 6. X equals +6. However, right here, see how it doesn't go just nicely straight through? It actually never goes through that x-axis. It doesn't intersect it. It just touches it right there. And does a U-turn. We call that being tangent to the x-axis. And when your curve is tangent to the x-axis, it means you have an even multiplicity. Meaning we have that root more than once. So x equals 6 has a multiplicity, and we're going to say of 2. Now, how do we know if it's 2, 4, 6? We're not going to worry about that right now. We're just going to say it's a multiplicity of 2, okay? So it's an even multiplicity because it doesn't go through it. It does a U-turn. It is tangent to the x-axis by just touching it at one point and going back up, okay? Even multiplicity, multiplicity of 2. If you just told me x equals -5, x equals 0, x equals 6 as solutions, I would be happy right now. Later, not anymore, but right now I will take it. What is the leading coefficient of this polynomial f of x? So the leading coefficient would always be when it is in standard form, it being the polynomial, right? Is my polynomial in standard form? Standard form means you have the highest exponent first, and then it goes down in decreasing order. So look at all your exponents. 6, this is a constant, this is 3, this is linear. So they're not in order. Let's rewrite that in order. 6 was the highest one, so x equals -6x to the 6. The next highest exponent will be the cubic here, so we're going to put the cubic term next. The following next will be the linear term, the x to the first power, so we're going to write our linear term, and then finally the constant. This one is always at the end. Alright, that does not change anything about my leading coefficient, but it gave us a good opportunity to talk about how to write in standard form any polynomial, right? Okay, leading coefficient. A coefficient, what is a coefficient? If we don't know that, we wouldn't know how to find the leading one. A coefficient is a number in front, or multiplied, I should say. It's a number multiplied to a variable. Okay, -6 and x to the 6 are tied by a multiplication, and so -6 is the coefficient of x to the 6th of that. So the leading coefficient is -6. So we're going to say leading coefficient is -6. I hope I didn't say x to the 6. I hope I didn't. The leading coefficient is the -6, which is the value we're multiplying that leading term with. Okay. What is the y-intercept? I'm going back because I think I want to make sure I use proper terminology. Leading coefficient is the number multiplied to a variable, and this is my leading term. The whole thing all together, the -6x to the 6th, is what we call the leading term. The whole thing is the term, and then the leading coefficient would just be the value that multiplies the variable, right? So leading coefficient is -6. Okay. What is the y-intercept of the polynomial f of x defined below? So the y-intercept, so where does a graph any graph ever cross the y-axis when x equals 0, right? So look at this one. The y-intercept is when x equals 0. Now that's a special case because they're both 0. But the y-intercept is when x equals 0. So what I'm looking for is, what is f of 0? Well, let's find out. So we're going to replace all our x's by a 0. So that's evaluating this function at 0. And obviously that's just going to be a 0. So the y value, your y-intercept, so therefore the y value of the y-intercept is y equals 0. Now, notice how I use the question words to write my sentence. I expect you to do that, right? I expect you to be nice and formulate your answers with proper sentences. The y value of the y-intercept is y equals 0. Actually, it's just 0. Because I'm already talking about the y value here. What is the degree of the polynomial f of x below? The degree is always the degree is the exponent of the leading term, but this is not written in standard form yet. So let's rewrite that in standard form first. So remember, we're looking for the highest exponent, which is this one. So that will be 8x to the 7. Then the next highest will be this one, so it's a quartic term, 5x to the 4th. Then we have a quadratic term, 5x squared. Then I have a linear term, negative 10x. And finally I have a constant, it doesn't have a variable. And now I can look at the leading term, and this will be this one, right? So my leading term is 8x to the 7th, and the exponent of the leading term gives me the degree of the polynomial. Therefore, the degree of f of x is 7. Almost done. Given the polynomial function f of x, we have two roots, and we're told we have a leading coefficient at -2, and we need to write a possible function. This is kind of important to notice. We don't say it's the only answer, right? It's a possible solution. But what we need to have for sure is two solutions, two roots at x equals 0, x equals -1, and a leading coefficient of -2, okay? So if I have a solution at x equals 0, well, that's already going to be one of my factors, right? Because there is nothing to move across the equal sign. I'm going to have another root at x equals -1. We're going to find the factor, so move that across the equal sign to set it equal to 0, right? So you do +1 on both sides, and that will be my other factor. So this one is already equal to 0, so this is my factor. And now I made this one equal to 0, this is my factor. So I'm going to have an x multiplied by an x plus 1, but I need all of that to have a leading coefficient of -2, okay? And that will be my f of x. I need to write that in standard form, meaning I cannot keep my parentheses. I actually have to get rid of all my parentheses. I really don't need those brackets, so I'm going to erase them. I mean, they're not wrong to have there, but they're unnecessary. So I'm going to put my 2x in the front here, because that's still just a multiplication, right? So I don't really need them. Okay, standard form. So we're going to distribute is what we need to do. Get rid of all your parentheses. So that will be -2x squared. Will be -2x, and that will be it, right? So the polynomial, make sure that when they give you a name, you use the name they give you to name your polynomial, right? You cannot change that. F of x equals -2x squared minus 2x will be our answer. This polynomial would have a root at -1, 1 at 0, and a leading coefficient of -2. Okay? We're switching gear now. We're going to exponential functions and equations, actually. When you have a variable in the exponent, you need to make sure you isolate that first before you try to do anything else. So we have a times 8 here. We're going to divide by 8. Don't try to switch that to a decimal yet. Just leave it as a fraction. So 10 to the x is equal to 1 over 8. At this point, we're going to solve that. We're actually going to have to take a logarithm on both sides. Okay? So what logarithm are we taking? We're taking the same base logarithm than we have here. This is a base 10. So I need a logarithm base 10. So I'm going to do log base 10 of 10 to the x equals log base 10 of 1 over 8. So remember, when we solve the equation, we have to do the same thing on both sides. And so I want to, because the inverse operation of an exponential is when your variable is in the exponent. Inverse operation of exponential is logarithm. And to find which logarithmic base I want, I'm going to look at the base of my exponent. It's a 10, therefore I want a base 10. If I had something like 3 to the x is equal to 81, for example, well, now the base of my exponent is 3, so now I would want a log base 3 on both sides. Okay? Alright, so how does that help me? When I have the same base as what's inside the exponent, this, by the way, can be brought to the front. Your exponent is always going to become a coefficient in the front, so I'm going to go write that first. Let's write that step down. This is one of the properties of logarithm. This we're not changing anymore. That's just going to be a big old nasty number. Okay, we're going to eventually put that in our calculator. When you have an exponent inside a log, you can bring it to the outside and make it a multiplication, right? So as a coefficient, so that's now becoming the multiplication. So then I have a log base 10 of 10. What this is saying is 10 to what power gives you 10? So what that says, log base 10 of 10 is asking 10, that's 10, to what power, what exponent gives 10? 10 to what power gives me 10? 10 to what power gives me a 10? Well, there is only one power that gives me a 10 out of a 10, and that's a 1, right? So this all goes to 1. That whole thing becomes a 1. So really what I have left now is x times 1, so just x, is equal to that big old thing. And I kept writing that base 10 here, but 10 is actually what we call, you can see, 10 is actually what we call the common logarithm. So we normally don't write it down. You know, it's like a square root. When you have a square root, you don't ever really write that 2 in there, although you know the index is 2. It's the same with a log base 10. We usually don't write it because it's the most common one. Well, besides the natural log, but that's something else. Okay, so I'm going to go to my calculator, and I'm going to, this will be a legitimate answer, by the way. I could stop here and say this is it, right? But I have a log key on my calculator, right? The log key, LOG, right there. And so I'm going to say I want to find the log of 1 over 8. So if you remember, fraction is alpha y, and then the first one is your fraction, so you hit the key number 1, and then put in your fraction. So 1 down 8, close your parentheses. And see, it gives you a decimal approximation, right? So that will be about negative 0.5 always give me 3 digits of accuracy after the decimal. So 903. Always 3 digits of accuracy after the decimal. Okay. Now, what if I didn't have a base 10 and I couldn't use just that log key? Because this key is only for base 10, right? What if I had this one that I wanted to figure out what that is? A log base 3. So for that, I'm going to go to my math key and I'm going to keep scrolling all the way down, all the way down, all the way down. See how here it says log base something? That's when you want to give a different base than 10. So you're going to say enter. You're going to put in your 3. And then you would put in your 81, right? I'm giving you this example here to show you. Close your parentheses and it will give you the answer. So this one was a nice number. So that's when you're using something that's not a base 10. Right, last problem. Yes, that's our last one. Last problem, and this is long video again. I need to solve this for x. So what I want to look at first is, do those two numbers have something in common? Well, 36 we know is the square root of is 6 times 6, right? So 36, I'm going to show you, divided by 6 is 6. So I know I have a factor of 6 in that. So this is the same thing as 6 squared. You agree? I hope you do. 216, well, I don't know. Let's try. 216 divided by 6 is 36. And when I divide by 6 again, I'm going to get 6, right? So 216 is actually 6 times 6 times 6, which is 6 cubed. And that's equal to 2x plus 2. So I'm rewriting my two bases so that they're alike. Now, why do I want to do that? Because now I have a power to a power. We've done enough of those. We know that will be multiplied, so that's a negative 6. Power to a power. Ooh, I have more than one thing here, so I'm going to have to distribute. So that will be 3 times 2x plus 2. Okay, we're going to leave it like that for a second. I have a 6 and a 6. So when the bases are the same, the exponents have to be equal to each other, because I'm telling you it's equal, right? That's an equal sign. That's equal to that. And because 6 equals 6, then those two have to be equal. So I'm going to take that down and say, oh, then 6 has to be equal to 3 times 2x plus 2. I lost you. Here you are. And now I'm just going to solve like a regular equation, right? So negative 6 equals 3 times 2x plus 2. You're going to distribute that 3, so negative 6 equals 6x plus 6, right? We just distribute here. I'm going to subtract 6 from both sides. So negative 12 is equal to 6x. Divide by 6 on both sides. And x is equal to negative 2. All right, we did it. Whew, study hard. Be ready.